Okay, so logarithms. I'm adding a little bit of extra material up here in the corner to remind you of the algebra of logarithms. When you have the log, first of all, we're using ln, which is the natural logarithm. So when you have ln of a times b, you have the sum of the logs. When you have ln of a divided by b, you have the difference of the logs. And when you have ln of a to the power b, you bring the power in front, and it's b ln of a. And then when you combine ln and e, they are inverse functions. So ln of e to the x is x, and e to the ln of x is x. And ln of 1 is 0. Those are the important things for right now that we will actually get to in a little bit. As far as the calculus goes, what you need is the formula. So if I have f of x equals ln of x, then the derivative, f prime of x, is 1 over x. All right, so that is your formula for the derivative of the log. Now, if I have a composite function, all right, so suppose I have, all right, let me go back to the d dx notation here. It's easier to write this down. d dx of ln of some function, f of x. Right, then we're basically applying the chain rule. So the chain rule is I take the derivative of the ln, and then I take the derivative of f. So the way we usually write that is like this. We do f prime of x over f of x. That is the easiest way to remember it. Okay? All right, so we have these formulas. I am going to take a look at some examples. All right, so the first two don't involve the chain rule. They're just basic log examples. This first one right here is a product, and the product is right there. All right. So when I put the derivative of this one together, I want to put it together with the product rule. So I'm going to go f prime of x is going to be first x times the derivative of the second, ln of x, plus the second, ln of x. Actually, I should be consistent with my parentheses if I'm going to do that, times the derivative of the first. Right, so that's going to be x times the derivative of ln of x, which is 1 over x, plus ln of x times the derivative of x, which is 1. All right, so when I put together x times ln of x, I get x over x, which is 1, plus ln of x times 1 is just ln of x. All right, and that is the answer right there. All right, come over here. Let's do this one, g prime of x. All right, this one is a quotient. So I'm going to put it together with the quotient rule. So the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. All right, so I get x times the derivative of ln of x, which is 1 over x, minus ln of x times the derivative of x, which is 1, all over x squared. Here again, I multiply x times 1 over x, I get x over x. So that's 1 minus ln of x times 1 is ln of x, all over x squared. Which again, that's as far as I can go with that. So there is the answer to that one. All right, so those are the basic problems. Let's get into something that's a little less basic. All right, here are a couple of problems that are going to involve the chain rule. All right, this first one right here, when I take the derivative of this, I have ln of something that's not just x inside. So that's a chain rule problem. Now the nice thing about the ln is the chain rule kind of falls apart really, really easily. All right, so when I do f prime of x, all right, I take the derivative of the inside, which is going to be 2x, over the inside, which is x squared plus 1. And basically that's it. All right, it's very, very straightforward. All right, the derivative of the inside over the inside. Okay. When I look at the second one, the issue that I have here is taking the derivative of the inside. All right, that's a fairly complicated expression. It does involve a product rule, and inside that product rule, I'm going to have a chain rule. I'd like to avoid that if I can. This is why I reminded you of all those log rules at the very beginning. One of the nice things about logs, and actually the reason we want to be able to take derivatives with logs, is that I have all those nice log rules. Right? So before I do any calculus to this, I am going to use my log rules to split this up. All right, so I have ln of a product. So I've got the log of a product, so that becomes the sum of the logs. So that becomes ln x squared plus 1 plus ln of x to the third plus 2 to the sixth. All right, so right off the bat, I've gotten rid of the product rule issue that I had here. Now I'd like to get rid of the chain rule issue that I have with this one. So I have the rule that says if I have an exponent, it can come in front here. All right, so this is going to be ln of x squared plus 1 plus 6 ln of x to the third plus 2. All right, so what I've done is I've taken an expression that's fairly complicated here to have to take the derivative of, and I was able to break it up into individual log problems. And each of these individual log problems is just like this one over here. All right, so now when I go to take g prime, I'm going to work from this version here, this last row that I simplified all the algebra on. And I'm going to use my basic log rule, derivative of the inside over the inside. So ln of x squared plus 1 becomes the derivative of x squared plus 1, 2x, over x squared plus 1, plus 6 times, same thing here, derivative of the inside over the inside. So the derivative of x to the third plus 2 is 3x squared over the inside, x to the third plus 2. All right, so about the only thing that I would want to do here is I'm just going to clean this second one up. All right, so I've got 2x over x squared plus 1 plus 6 times 3 is 18, so I'm going to have 18x squared over x to the third plus 2. All right, and that is my final answer on that one. All right, so you want to be able to use those log rules when you have something complicated inside a logarithm to draw it out, to break it apart so that I'm dealing with individual logs, and then I can just use the log rule for taking the derivative, which is very simple. Now, if I take this and I combine it with our ability to do implicit differentiation, which I think is what the next example is. Hang on, let me see. Yes. All right, let's take a look at this function. I tried to pick a function that was about as bad as I could make it. if I want to take the derivative of this, all right, take a look at what's involved in this. This is a fraction, so it's a quotient rule. So it starts off with a quotient rule. At some point, I'm going to have to take the derivative of the top. That top is a product, and inside that product, I have two chain rules. All right, so if I were to try and do this the way it's written, all right, it is a quotient rule that inside of which involves a product rule. Inside of that involves two chain rules. That's a lot of algebra. It's a lot of messy algebra. And to be perfectly honest, I don't want to do it that way. All right. So we have a technique that's called logarithmic differentiation. And what it involves is I have a function, so I have an equation. I can take the log on both sides of an equation. That's one of our log rules from algebra. So if I, instead of writing f of x over here, if I take that out and I replace it with a y, okay, my eraser has decided it's going to stop working, so I'll just rewrite it. I replace that with a y. What is this? X squared minus 2x plus 3 to the fifth. And I guess it's good because in this case, I want to rewrite this with a numeric exponent, so I can do that here. 2x minus 3 to the 1/2. Okay, so I write the y instead of the f of x, and then I take the log on both sides. So on the left, I'm going to say ln of y, and on the right, I'm going to say ln of this whole mess here. One more time. Okay. All right, so I'm going to leave the left side alone for a minute, and I'm going to work on the right side. All right, so I have a division problem, right? I have a quotient. So my rule says that I can take the log of the top, ln of this, minus the log of the bottom. All right, now I'm going to leave that alone for a minute, and over here I have a product. All right, so I can break that product up, ln of x plus 1 to the 7th plus ln x squared minus 2x plus 3 to the 5th minus this term here. All right, and then the last step that I want to do is bring all the exponents in front. All right, so I'm going to rewrite on the left-hand side now. I have ln of y. On the right-hand side, again, each one of these I'm going to bring the exponent down. So that is going to be 7 ln of x plus 1 plus 5 ln of x squared minus 2x plus 3 minus 1/2 ln of 2x minus 3. All right, so I've used my log rules to break that left-hand side down into 3 individual logarithms. Now I can use implicit differentiation to take the derivative on both sides here. I'm going to just scroll a little bit so that I can have a little bit more room here. All right, now when I take the derivative of this, I have to take the derivative of both sides. All right, so the derivative of this side and the derivative of this side. Remember, y is a function of x. So when I take the derivative over here, I have to use implicit differentiation. which means I have to take the derivative of the inside. All right, so the derivative of this is going to be y prime over y. That is the log formula. Over here, I get 7 times the derivative of the inside over the inside. 5 times, again, the derivative of the inside, 2x minus 2, over the inside. Minus 1/2 times, again, log, so the derivative of the inside over the inside. All right. Now, before I do anything else, I want to clean up my right-hand side. So I'm going to leave the left-hand side as y prime over y. This is going to be 7 over x plus 1 plus, I guess I can just multiply that out. We'll say 10x minus 10 over x squared minus 2x plus 3 minus, now here I've got a 2 on top and a 2 on the bottom, so that's going to be 1 over 2x minus 3. So I think I've got that simplified enough on that side. All right, now remember I need to solve this equation for y prime. All right, so y prime, right, multiply both sides by y. So I multiply this side by y, and I multiply this side by y, and I get y prime equals this again, which I have to write again. Okay, all of that times y. All right, now what is y equal to? Right, if I go back up to the top here, sorry, I think a muscle car just went past my house. What is y equal to? Y is equal to that. Well, let's do this one. Y is equal to this up here. All right, so when I put y back in, all right, I think I can recreate that. I'll do it from here. Okay. So when I put y back in, this y right here is going to be x plus 1 to the 7th times x squared minus 2x plus 3 to the 5th all over the square root of 2x minus 3. All right, so this is the answer to finding the derivative of this monster right there. All right. I know there's a bit of algebra in the beginning using the log rules to break it up, but trust me, it was a lot easier to do that than it would have been to try and apply the derivative to that algebraically. All right. So the whole point of logarithms is really this technique right here. Right? You want to be able to take the derivative of the log function to be able to use it to do logarithmic differentiation.